Welcome to a new episode of the Unicorn Bakery. My name is Fabian Tausch, and today we're talking about quantum computing, how to sell complex products, and more. Alex Keesling is the founder of and CEO of QueRa, and QueRa is a quantum computing startup, state-of-the-art quantum computer with 55 qubits developed at Harvard School as a research project and then turned into a business. And Alex was a researcher himself before, turned founder and CEO. And QueRa is currently state-of-the-art. It's possible to book QueRa quantum computing capacities through AWS, which is quite interesting because it's probably the most available quantum computing product at the moment. QueRa also recently got the confirmation from the Japanese government to place and deliver a quantum computing system to Japan for the amount of $41 million, approximately, plus minus. But this shows that in this business there's a lot of money for the complex projects, but also we're at the forefront and the beginning of the technology from a perspective that we don't have the ChatGPT-moment yet. So probably you and I, we don't experience quantum computing that often in our day-to-day life, but it will come at some point. Alex predicts it to be probably the end of the decade, so 2029, 2030. And therefore, here is a first glimpse into quantum computing, how to build out of university a research project into a company, and also how to sell complex products and find your product and message market fit. Here we go with Alex Keesling from QueRa. Alex, welcome to the Unicorn Bakery.
Thank you, and thank you for having me, Fabian.
I think there are a lot of topics to cover, and the one thing I'd love to start with is your way from researcher to CEO. I think it's not like 100% trivial for a lot of people, and probably also not for yourself. How natural was it for you to turn the back to research and become CEO of a venture-backed company?
Yeah, I mean, it was, of course, a big step, but it's not random, right? It came from having developed the technology as a researcher that we are now continuing to push forward and commercialize here at the company. So I think it is an abrupt transition, but the people that I started working with when QueRa started are very much the same people that I knew from my days as a researcher. That's how the whole thing started. It is we're working on a completely new technology that requires very in-depth and specialized knowledge of tools that so far have been primarily the realm of research. So coming to the company to lead it and to transition from an individual contributor as a researcher to someone that is at the helm of the company, there's a lot that I had to learn, and I would say there's a lot that I'm still learning. And what was very important and continues to be very important for me has been to surround myself with a great team, some of whom have a similar background to myself and have been, spending years of their lives developing technology in research labs, but also some of whom are advisors and board members and, all sorts of other positions and functions that have seen the process of building a company, of transforming it, of growing it, of taking technology from its inception all the way to product and maturing it through that. And having access to that network of advisors, of coworkers, that is really what makes this possible. there's a lot to learn, but I think that will always be true no matter what your background is. And the only way to do it is to form that community that is making it happen and that is supporting it. So, it's been a wild ride, and it's really possible because of the community.
Which commonalities did you find between being a researcher and running a company as a CEO?
I think that both in their own way are hard work and long hours and rely very heavily on community. I think that there's, for a lot of people, there's a conception that researchers are very isolated and they work as lonely geniuses, but that's, in my experience, that is very far from the truth. There's a lot of science at the end of the day is a human endeavor and comes from people talking and working together and having to put away, differences to find what the best solution is to move forward. And all of these things, I think, are the same no matter whether you're doing research in a lab or whether you are guiding a company. At the end of the day, there's a goal that you're trying to achieve, and you have a team that is supporting that. In this case, I am, of course, leading this team and setting the priorities, but it all comes from the same kind of very systematic approach to what is the goal, what are the challenges to get to that goal, how do we find creative solutions. And I think that's another thing, that there's in research, there's a lot of room for creativity. And creativity is exactly what you need when you're being faced with something for the very first time. Another thing that is important that carries over from research is understanding that while you might not know the answer, the answer might be out there. And being resourceful and knowing how to find information and how to reach out to others to seek for that guidance, that is very important. There is a difference, I think, in between that world of research and being a CEO of a company. And I think it's both a difference of scale and a difference of time. Of course, the scale at which we do things here is very different than anything I ever did in a lab. The amount of people that are contributing towards the goal, the coordination that is necessary, the types of backgrounds that people have, and understanding how to create functional teams that leverage each other's different backgrounds and that can make progress better together. But it's also a matter of time. In research, you, of course, always want to be moving fast, but the external pressure is often much smaller, whereas in a company, we are trying to get things out fast, and we have to commit to dates, and decisions need to be made very quickly because, again, this difference in scale, the amount of people that are relying on this and that have access to the service that we have, the product, and even within the company, this all makes it so that decisions need to be much more timely. I guess another way of thinking also about this difference in scale is when doing research, while its impact might be broad in the future, the research is really immediately affecting basically only those that are working on it. Whereas here at the company, we have a product that we have made available to customers. And suddenly the number of people that rely on us executing on our plans is much larger. And they have much less control than other researchers would over the output of what they're getting out.
One question in between, because you mentioned there are a lot of there's a team relying on decisions in the business. There are customers relying on or also touched by everything you decide. What are the current involvements? Like, how many people are working for QuEra? How many customers do you have? Like, just as an overview, that somebody who listens and hears about you the first time understands where you're currently at.
So at the company we have over 60 employees. We've been steadily growing since inception. In terms of customers, we actually have different modes of access. So our first quantum computer is available on the cloud through a partnership with Amazon. And this gives access to a very large number of users. So anyone with an Amazon account can go to the Bracket website and start sending jobs to this quantum computer. So we know that we've received jobs from very, very many different unique customers. Besides from that, large-scale cloud access, we also engage with customers on a more direct partnership to help them understand the capabilities of quantum computers and how to take their use cases and convert them into programs that can be run on the quantum computer. And for this, we've worked with some large companies in finance, in energy. This is a much more handheld approach, and therefore the number of customers that we reach in this way is a lot smaller. It relies on very deep engagements with our application scientists. So over the years, we've had, probably on the ballpark of 20 or so of these engagements. And recently we've realized that there's an appetite to get access to quantum computing, not just through remote cloud access, but also by installing quantum computers in place on third-party premises. And for this, we haven't yet delivered our first systems, but we are going to be delivering one to the UK and another one to Japan. And this is yet another way to reach many more users of quantum computing. Because while we are working with the institutions that are purchasing the hardware itself, we are also partnering with them to create successful programs that give access to more users to these systems.
I think just for listeners to get an understanding, because it's publicly on your website, for example, delivering a system to Japan is approximately 41 million USDs in volume, just that people can understand that that's not like, it's an easy thing. I think that also takes some time, and we can talk about the complexity of delivering in a second, or probably we do it now. Like, what's the complexity currently to deliver a quantum computer to, for example, Japan?
Yeah, it's a great point. This is cutting edge technology, which it is a computational tool, but it might not look anything like what you expect a computer to look like, right? It's not anything like a laptop, and the process to build and operate quantum computers is very different. I can tell you that, I can tell you that the way that our first system was built was very much in line with how experimental setups at universities are built. This required a lot of PhD trained physicist to place optical elements on a table very carefully and fine-tune them by hand. And to operate it similarly, it initially took a lot of active oversight of the system. And over time, we've kind of pushed the design and the engineering along, so that now our systems are much more streamlined in how they're built and much more automated, so that the operation is a lot more seamless for users. So our current systems are about the size of 1 to 2 dinner room tables. They're quite large still. The basic premise is that while all of that can be simplified and made smaller over time, the big race right now is to get better capabilities. And that is what we're providing. So one of the biggest challenges, since you're asking, is that we're taking capabilities that are really cutting edge, that are just being demonstrated for the first time this year or just a few months ago, and converting that into product. So we're really reducing that timeline to productize new developments. And we need to do it in a way that allows the system still to be stable, robust, and deployable. So the system that we're going to be delivering to Japan, this is going to happen next year. And there's a lot of work in preparing both the surrounding infrastructure for the quantum computer to be installed, as well as doing all of the testing and validation of the full system here in our offices in Boston before sending it and then rebuilding it on site. So it is quite a large effort, and this is a process that is being developed today because, again, this is cutting edge technology and no one has done something like this before.
So just to get a super clear understanding, you're building the quantum computer in the lab or in the office, depending how we want to call it, but probably somehow both. And then you're taking it apart, sending it to Japan, and then rebuilding it after you know how to put it together?
Yep, that's right.
Okay. Because, sometimes hard to understand like how this actually looks like, as it's not, oh yeah, we know what we do, we just do it 100 times, here we go. So
there's only very few systems even remotely like this one in the world right now. And most of them have been built over years in university groups.
What would you say, how many are currently there?
There's probably about 20 or so across universities that are actually functional in terms of just the basic core functionality of being able to manipulate individual atoms at the scale that we do. But fully functioning quantum computers, there's really been only, outside of what we're doing here at QuEra, there is a system at Harvard University, which is what I developed during my PhD, and that has continued to evolve. That is the most advanced system that has any reported utilization. But what we're going to be delivering to customers is going to be basically that, and it will be the first ever commercial system with that kind of flexibility and performance. So this actually will be the first of its kind.
I think one question that we have to ask right now, because I'm very sure that not everybody knows what a quantum computer is, and I also can't explain it myself. How would you explain what a quantum computer is to a 5-year-old?
Yeah, so maybe I'll start with a 5-year-old and then move to slightly more complexity. But so I think it helps to start with that comparison. And a quantum computer is a computer that has a different set of operations than what we all know as computers. And that means that it is fundamentally different. So instead of, think of the difference between a pocket calculator and the most advanced supercomputer in the world. They are more like one another than that supercomputer is to a quantum computer. Because again, the calculator and the supercomputer follow exactly the same set of rules. One of them is just larger and more complex. But the quantum computer has a different set of rules. And while this is, a concept that came about in the 80s, it has taken a very, very long time to be able to build actual functioning quantum computers. And we are honestly still in the early stages of what they are and what they will look like. Now, the reason why it's different is because a computer works with bits, and they can be whatever physical representation you want, but it's something that it's either a 0 or a 1. And it's deterministic. The bit is always a 0 or a 1, and the way that it affects other bits in a calculation just depends on whether it is, again, a 0 or a 1. For quantum computers, and everything that will come after this is non-intuitive, and this is not because I'm trying to obfuscate, but just because it has taken us a very long time to even get our heads around what quantum mechanics is, and quantum mechanics or quantum physics is the basis for quantum computers. But it turns out that we can create quantum bits that are things that are 0 or 1, or something that is a combination of a 0 and a 1. And I think that a lot of people's first reaction is to say, well, okay, but that's just an analog system, right, that has a continuous value between 0 and 1. And it just gets more complicated than that, because when you look at the output of a quantum computer, it is every quantum bit at the output is either a 0 or a 1. So it's not that you can just treat it as some continuous analog value between 0 and 1. And these quantum bits can create basic operations between each other that are just not something that we can describe classically. And there are three important concepts. The first one that I already mentioned is this kind of being some combination of 0 and 1, and this is called superposition. The second concept is that the superposition can be something actually very complex that we call an entangled superposition. And an entangled superposition, which is the core that makes quantum computers really different, is that two qubits or quantum bits can now have correlations that are beyond anything else that we can see with classical. And the way that we first found out about this was through kind of mathematical explorations from Einstein, where he realized that two entangled, in this case we'll call them qubits, separated by many light years of distance, could be made such that observing one and seeing whether it was 0 or 1 immediately determined the outcome of the other one light years away, without having that light speed time to affect it. So I know it gets a little bit difficult to follow when we talk about quantum computing, but the fundamental thing is that it has different rules. It's an expanded set of rules, and it leads to programs where a quantum computer can be exponentially faster or more resource efficient than classical computers for some problems. And what this means is that if you want to take a perfect quantum computer and represented using classical computers. Today with my laptop, I think I can fully predict the outcome of a general purpose quantum computer that has about 20 quantum bits. If I wanted to do the same thing for a quantum computer with about 55 quantum bits or qubits, I would need to use the largest supercomputer in the world. If I wanted to push that to 56, I would need 2 copies of that massive supercomputer and connect them together. So the scaling here becomes just infeasible. And getting past those numbers with very good quantum computers above 50-some quantum bits, that gives us now access to potentially solving problems that we will never be able to address with classical computers. So there are some problems that we solve inefficiently today that we know quantum computers will be able to do with fewer resources. There are some problems that today are basically impossible. And for some of those, quantum computers will help us get to meaningful solutions and really think about how many of these impossible problems we can start tackling. And some of the ones that we are very interested in are in, for example, chemistry and finding new catalysts or better materials, for example, for batteries, for energy storage. There's a lot of work that we do today that relies heavily on being able to predict the properties of the things that we build and that we create and that are the underlying workhorse for our industrial society. But I think that having access to large-scale quantum computers is going to advance that faster than we have ever imagined so far.
Quick insertion here. Of course, I had to ask ChatGPT because sometimes it's easy to ask and then hear your answer as well. How would you explain a quantum computer to a 5-year-old? And the answer is quite short. Imagine you have a very special kind of toy box. In a regular toy box, you can only play with one toy at a time. But in this special toy box, you can play with many toys all at once, in many different ways. A quantum computer is like that special toy box. Regular computers can only do one thing at a time in a specific order, but quantum computers can do many things at the same time. This makes them super fast at solving really hard puzzles, much faster than regular computers.
ChatGPT is great at what it does. And I can actually tell you a little bit of the subtlety there, and that's that this idea of playing with all of these toys simultaneously, this is what I was describing as superposition. I mentioned that there's 3 important concepts. Superposition, which is this doing many things at once, because you're both 0 and 1. There's entanglement, which I mentioned as this unique quantumness of the doing many things at once. And there's another one, which is interference. And the reason why interference is important is because this description from ChatGPT is great up to the point of, well, but then what happens after? Because a computer, you give it some input and it gives you some output. And you cannot understand this output that is all things at once. So the way that a quantum program works is that we give it a simple input, and then it uses this superposition to create, say, all of the possible approaches at once. But then if we just look at an output, we're going to get a random output that picks only one of those. So the importance in building useful quantum algorithms is to use to use interference between all of these possible programs, so that the ones that are not the ones that lead to the right answer start disappearing, and at the end you end up with deterministically a single output, which is the correct solution to the problem that you wanted. So by putting together superposition, entanglement, and interference, that's how you get a quantum computer to be useful. and to actually give you something out of this, playing with all toys at the same time.
At some point I talked to Markus Pflitsch, who's building Terra Quantum here from Switzerland, I think. And he described, for example, one use case that I can just easily imagine. If you gave me the task to find the highest mountain mountaintop in Europe, for example, I would have to run around one mountain after another and figure out oh, this one is the highest. No, this one is. And with a quantum computer, you could, for example, throw a layer completely over Europe and lower it from as high as possible to figure out, and the first time it touches a mountaintop, I think it's the Mont Blanc then in Europe, it touches the Mont Blanc and says, hey, I saw everything in Europe, I covered everything. This has to be the highest position, the mountaintop, so we can stop the experiment. We're already done because we know there is no higher mountaintop. And this was quite easy for me to at least understand what it looks like in action.
Yeah.
In a very simple example, probably.
I like it. I think that the question is, how do you do that without, if you're looking for the highest mountain, you're just one person, right? And you're moving around. If you wanted to have a drape over all of Europe, imagine the amount of effort that you would actually have to put into coordinating all of these things. So the key of the quantum computer is that it's actually somewhere in between both, right? It's just you, but you're somehow able to explore all of these mountains simultaneously and kind of convince yourself about which one is the tallest in a much faster way.
I think it's just helpful to have more and more understanding on how this works. You mentioned we're currently probably at 55 qubits, and it needs one absolutely, or the strongest supercomputer that we have. 56 would need 2 of those. What is the inflection point where quantum computing becomes more and more accessible in the general public? Probably you don't like the example, I'm not sure, but what is the ChatGPT moment of quantum computing?
No, I love that because I know that somehow everyone knows about ChatGPT. And I think that will happen once we have quantum computers with a few thousand good qubits. And I'm using the word good here in a little bit of a loose way, but the important underlying concept here is that with a computer like my laptop, right? I don't have to ever think about whether my laptop is doing things right. It just does. The probability that it will introduce an error throughout the computation is very, very low. With a quantum computer, we can build things with now, let's just pick a scale, about 1,000 qubits. But these qubits are noisy and they introduce errors throughout computation. So when I say good qubits, what I mean is an effective qubit with a low enough error rate that it won't actually mess up the computation. And this is a super important concept. It's called quantum error correction. That's what the industry really needs to get us to that ChatGPT moment. And we're actually starting to see that for the first time now. So there were a few announcements last year, culminating with a demonstration led by a group at Harvard that we were collaborating with to demonstrate that it is possible to build and operate these logical qubits at scale, reaching up to implementing complex algorithms with about 48 of these logical qubits. And they need to keep getting better to get us to this quantum ChatGPT moment. But going back to the point of ChatGPT, I think that there's an analogy that I like, that when I think about how we got to that ChatGPT moment, I think that for me, as someone that follows only loosely the development of AI, in my life through popular media and so on, I've seen three major moments. One of kind of computers doing things that were in the direction of ChatGPT. The first one was, beating humans at chess. It was kind of like, maybe expected, but still a difficult benchmark to meet. The second one was, and I don't think that it had many commercial applications. The second one was beating humans at Go with AlphaGo. I think that one surprised people a little bit more because of the complexity of that game and how it actually went about beating humans. And the technology that went into that got a niche market through, for example, AlphaFold, that is now the best way that we have to estimate how proteins are folding and how that gives rise to function. And then the third one, ChatGPT, when somehow suddenly it became a product that is providing now value to multiple people in very different walks of life. And I think that there's an analogy here with quantum computing in terms of like the hardware capabilities. That first inflection point, as I mentioned, is something that I think we're seeing right now, the equivalent of beating humans at chess, which is being able to implement error correction and make the qubits work better. And as I said, this is just happening right now. The next inflection point that I see is, when do we have systems that are good enough at a large enough scale that we're past what classical computers can do, and we can start finding the early applications that have commercial value? And for me, this is where we hit about 100 of these logical qubits that are good enough to run complex algorithms. And that is because, again, we're going to be much past the era of what classical computers can predict, and we can start applying it to problems that maybe are very well suited to the type of hardware that we're running. Things where, again, like materials problems, where the complexity arises actually because of the quantum mechanical nature of things like atoms and electrons. And I think that's going to be kind of the similar equivalent to that AlphaGo moment. And that third point of ChatGPT, I think this is going to happen once we reach a few thousand logical qubits, where we already have a few programs that we know quantum computers of that size could be able to run, that would basically be running in the background, and people would have access to them probably without even knowing, because all of these things could be in a data center, and you could be connecting to some interface from your phone, and some complex calculation might be being sent to a data center without you having any idea of what's happening through the internet.
Yeah, fair enough. I think it's helpful to get a bit of an understanding, like where we're currently on the trajectory, to know and have a few thoughts and develop the mind for, like, okay, probably at this point in my life I could get there. Like, just what would you say, when do you, like, from a timeline perspective, knowing that it's a bit of guesswork and not like 1,000% predictable, like, what would you say, when is inflection point 2 and when could be inflection point 3, even when it's even more uncertain than inflection point 2?
Oh man, I could talk about this for like an hour and a half, but so
I give you a minute or two.
for the next inflection point, we actually put out a public-facing roadmap for our technology development over the next few years, early this year. And we are actually expecting to get to 100 logical qubits by the end of 2026. So we're moving very fast. There is now a clear line of sight for how one of our quantum computers is going to have to look like to be able to run these complex algorithms on 100 logical qubits. And that is, in our plans by the end of 2026. Now, getting to that last inflection point, I think that there the answer is still a little bit more open. There's some more work that we need to do on the engineering of the hardware, on developing the right type of applications, the models for integration of classical with quantum hardware, and there's a lot of co-development that needs to happen between the quantum software, the quantum hardware, how we implement quantum error correction. I would say that we could see these capabilities start to emerge before the end of the decade. As you say, predicting the future is always, a difficult endeavor. But I think that before the end of the decade, we could see, our QuEra computers with over 1,000 logical qubits.
Cool. Sounds exciting. One question that I had in mind regarding the researcher turning CEO and also like bringing all the capabilities to life for others as well. What would you say were the circumstances that made it possible to make a business out of a research project? Because I know that there are a lot of researchers out there that are thinking, hey, why, that are probably thinking, yeah, I'm not sure if I want to do a business, or thinking, hey, probably the circumstances are not right. Why was it, or were there the right circumstances or the right help, for example, also from the university to make it possible to build a company out of it?
I think that the first somewhat, not unique, but somewhat rare set of circumstances is that there was an emerging market for this technology. Not because the technology was really developed, but because there was an understanding that it is going to be revolutionary. It really will change how we think about what problems are solvable and how we think about computation. And we had started seeing some glimpses of how a quantum computer might be built. Now, this together with also an understanding that one of the applications for quantum computing might be important for, say, financial institutions and governments across the world, because turns out that quantum computers might be good for factoring numbers, or will be good for factoring numbers. And that is at the core of how we protect security in many ways today. So both of these things together, the kind of the hope of everything that quantum computers will enable, and also the understanding that the technology could have implications for other areas of life, like security, brought a lot of interest groups, investors, companies that want to incorporate quantum computing into their workflows in the future, governments, all together to say this is worth looking into, investing into, and that's when you saw, for example, the very large tech giants start to create their internal groups to work on quantum computing. So timing is really important here. That there was an interest, that there was capital put behind it, that there was a shared understanding that the technology is important. And that is the first and most important factor. If you have a great technology that you don't know who's going to benefit from and no one else sees a potential benefit, it might just be that it's a matter of time until there's a better match that is found. So for us, having this emerging quantum industry was very important. Besides from that, I think being in the right place helps. Boston has a history of innovation and of supporting that innovation, and working with the universities to help us spin out the technology into a company, and working through the Office of Technology Development and others to set some structure, together with being able to tap into a network of entrepreneurs and investors in the area who are very, very willing to jump in and help and give us guidance. All of those things were very important. Of course, there was also, it was important that there was a team that was excited and ready to take the plunge and say, we're going to do this and we're going to make it work, and we are going to find a way to take this technology outside of the lab, put it into people's hands, and continue maturing it. That is, of course, very, very important because, as I mentioned, at the beginning, it's really about community and the people you work with and the entire supporting structure.
What about finding the first customer or customers? Because I think on the one hand, it's a technology, as you mentioned, that's currently developing, but still in the early stages. Like not in the early stages of like it's getting started at all, but like still compared to, let's say, public perception. So how aware is the customer? Was the customer base already? How much education is needed to I'm not even saying convince somebody, but more like to create business cases together. Mm-hmm. What was the state of art when you started with QueRa?
Definitely a lot of excitement and intrigue, but it takes a lot of customer education. I think that everyone comes at quantum computing with slightly different ideas, and sometimes the first thing that we need to do is to start having the conversations of, look, here's why we think this could be very exciting for you, but also let's talk about what is the current state of the technology and how, as with every other technology, yes, this I mean, well, actually more than many other technologies, I think that this is going to be revolutionizing, but it's still not magic, right? It's not that you can just throw any problem at it without thinking about it. So let's work with you to understand what are the kinds of things that keep you up at night. Where would you like to find efficiencies? What are things that you would like to do that you have not been able to? And from there, spend the time with customers to say, great, we understand there's a few types of problems that you're looking at. We think that problem A has the best kind of adaptability for us to turn into a quantum algorithm. So let's work together on that. Let's do a quick, proof of concept, and then let's work with you to develop internal capabilities at your company, and we'll work together on implementing an algorithm, and also training you to think about quantum computing in a more helpful way, and to continue working with us as we develop the technology and as we continue to give you visibility into the types of capabilities that are to come, to start expanding the set of use cases that we can test. So it definitely is a lot of education. We're not doing this alone, of course. As I said, there's a growing industry, so there are many other companies that are doing the same as we are, and that's helpful because the technology being still early stage, many customers are looking for exploring different approaches and comparing the output that they get with different vendors. It also helped us a lot to partner with a very large company, with Amazon, to provide access to our system, because this gives users both visibility and an easy way to access it. So that lowers the barrier to entry, because they don't necessarily need to commit to a project together with QueRa. They can test something on the cloud and then come back to us when they need more, a deeper relationship to help them set things up for success. One thing that we've also seen recently is a growing market for purchasing full systems. So again, not just accessing the computers, but purchasing full systems. And one thing that we learned there, it's teaching both ways, teaching customers about the potential benefits of quantum computing and how we can help them, but also learning from the customers about what is it that really matters to them. And one thing that we have learned is that for the most part, people don't want to buy a quantum computer as a black box that they just get to install, because there's a lot of work still to be done on who will benefit most from having quantum computers, how are they going to use them. So really, the customers want to create partnerships and to build programs together where we can provide the hardware, and the hardware can be, the thing that attracts interest, that attracts users for them, but in a way that we can continue to support that work so that it is successful, so that customers can benefit from having access to these capabilities, and so that the other side benefits that they are looking for example, in the case of government-funded programs, they're interested in developing a local economy, and having workforce training is important to them, and having QueRa partner with them to help bring more knowledge about quantum computing, to train local people to know how to operate quantum computers, to partner with, for example, algorithm developers that are accessing the resources locally. All of that is coming from a deep partnership between us and our customers. So it's been a lot of work in educating customers, but really more in listening to their needs and adapting how we go about our business to support those needs.
I have a few questions on that. So the first part, selling very complex products has, let's say, pros and cons. I would say one of the pros is not everybody can sell it. Like, not everybody can produce a product. Not everybody can deliver, even when they say they can. So there's the potential for a huge differentiation. Mm-hmm. The second thing is it can take some time until you are at a stage where it's so productized. Like, for example, the AWS product right now, when I buy QueRa through AWS, is productized to a scale where I can just start setting it up, comparably to buying a full system. Right. That's so how do you get from I know what I can offer to finding the right message market fit and actually understanding what at least the most of the customers want to buy, because that's the hardest part, finding a message because you want to scale your product sales at some point, of course. Mm-hmm. With such a technical product, knowing that it's an industry that will develop further, I think you're also looking forward to with a more educated market, more use cases are known and more people know why they want the product. But for now, as a company, it's still the hard part, the balance between, we know what we can, but what is the core offer that we position in the market, because the market already tries to understand. How was your journey to figuring that out?
It was a lot of, there's no shortcut, right? We know what we can do, and we know what we will be able to do in the future. And what it takes is talking with a lot of customers and hearing what they need, and then bringing that back and adapting both the tech development to get to what customers care about more quickly, to adapt the messaging, to come in with the use cases that we prepared that are more aligned with the particular industry based on what we learn from them. To also leverage the success stories that we already have from working with customers to be able to say, yes, we can do this. And not only can we, but we've already done it before. And here's how it can help you. And kind of lowering a little bit the barrier of how much they need to dig deep to figure out, well, is there something that could help us? But to really be able to come in prepared and say, here's a proposal of something that we think might be interesting to you. And we can start here and then take it wherever you prefer. So yeah, it really is that early stage, learning from customers by just talking to as many as possible and adapting based on what we hear. Adapting the tech, adapting the messaging, adapting the customer targets even that we go after. And now that we're entering also this different approach of selling full systems, it's again starting over by understanding, as I was saying, what is it that really matters to them, and how can we build this to be a story of success for both sides over the long term, so that we can create a user base that continues to grow with us and that has a way to influence the tech development over the future. And sometimes this means hardware, but sometimes this means also the software and how, just to give you an example, we started out with an open source package called Blockade, which is very good at emulating some of the quantum processing that can happen in a computer so that it can help users get up to speed with how they would program our first device, the one that is available on the cloud. And it was written in Julia, because Julia is a great programming language for efficiency. But we had to adapt from learning that most of our customers had much easier access to programming in Python. So we had to create a new entry point through Python. So it really is that. It's in terms of tech and capabilities, we know where we are, we know where we're doing, we're communicating this to customers, but it is the much bigger job is to learn from them so that we can find where we can add value.
This brings me to a next question. How many of the 60-ish people are in sales?
We have a small sales team. It's probably about 5 to 10% of the company. But of course, there's the sales team specifically, and then there's people that get involved in sales. And at this point, this continues to be a large portion of the company, right? Like, I am still talking with our customers, with potential customers. So are many other members of the executive team. We have algorithm developers, we have hardware developers, also jumping on calls with customers, understanding their needs, guiding them through how to use the systems. So yeah, that's the full picture.
Why I'm asking is because it's such a complex product where I'm thinking about, okay, how important is the actual sales skill compared to the real technical understanding of what the product is capable to do? Because I'm currently thinking, what is easier to learn? To understand quantum computing, or to learn how to understand the customer needs and sell the quantum computing product? And my personal, very non-educated thought would be, okay, it's easier to learn the sales skills and get better at sales than understanding quantum computing.
We have both. We have sales learning quantum and quantum learning sales. And I think that's really what it takes, that and getting that extra support from technical staff, that their main role is not sales, but they are instrumental in driving sales, especially once we start getting towards defining a joint project, for example, where the other, our customers might already have a few people in their company that have a background in quantum or quantum computing, or that have been looking into this for some time now. And then it really makes sense to have that interface with technical staff that can, give them the confidence that, we have technology that works, we know what we're doing, and that can speak the same language.
So to not be reliant on people who know quantum computing inside out and are the perfect sales machines, you find, let's say, a hybrid way of combining and forming alliances, let's say task forces to out of like people who are sales, but also the technical understanding to then position the right, let's say, product for the problem that the potential customer has, so that you find a hybrid version that makes it easier for all of the parties involved in the sales process to deliver the best results.
That's right.
Okay. It's just interesting because I know, for example, even founders in fintech currently thinking about, okay, it's such a specific product use case, and thinking about, hey, do I hire people who understand the product better or the sales, or like, so this is a reoccurring challenge in not any business, but in a few businesses, and that's why with such a specific thing, it's even better to understand how you do it, because I think that might be a bit different than the typical SaaS scale-up that has an, in quotation marks, easier sales setup.
Yeah. Well, I think that this is something that, technical sales will always have some portion of that, technical know-how that is required.
So I think I should have asked most of my questions. Do you think we forgot anything we need to talk about?
I don't necessarily think that we forgot anything, but I think that, sometimes it's helpful to take a step back from, the nitty-gritty and just look at, it's such a cool, exciting time for quantum computing. I mean, of course, for me personally, but I think that we're seeing the birth of a technology in an industry that I think will have a very big impact in what kinds of things we can do, across the world in, within our lifetimes. And to be able to take technology that seems at first very esoteric and very, very research driven, and to be able to put that into people's hands and find the right applications and have those applications drive also the technology progression, I think it's super exciting. And we were talking about how difficult it is to predict the future, but I think it's difficult to predict it in both ways, right? I think that I expect that the progress that we're going to make is going to be, kind of exponential, and it's very easy to overestimate in the short term, but underestimate it in the long term. So thinking about the kinds of problems that we're seeing with customers that are interested in using quantum computing, I think that that's this first class of problems of things that we're already doing and we're basically using as a benchmark. But there's an entire space of opportunities that we haven't started even thinking about because we're just not tackling these problems. And I think that predicting how we're going to be using quantum computers in the future feels to me a little bit like trying to predict the impact of the internet today, but making this prediction in the early 1990s. So I think it's going to be a very exciting technology to keep track of and to get involved with for those that are interested in technology and we bring together expertise from so many different areas. We were just talking about sales, but we have physicists, we have mathematicians, computer scientists, mechanical engineers, systems engineers, all sorts of different backgrounds that really come together to make this possible.
I have two last questions. The first is if I'm a founder listening right now, or even a tech person thinking, okay, there's this AWS product that I can try out. What would be the easiest applications to test out QuEra and quantum computing?
It actually depends on the quantum computer that you're accessing today.
Probably the QuEra one when I'm saying AWS QuEra.
We have a lot of notebooks for people to get started on the AWS side on Amazon Bracket, and the first kinds of things that you can do are explore some of these underlying principles of what qubits are and how they work, and see what happens if you give an instruction to a single qubit versus what happens when you give an instruction to 2 qubits, and how you can start implementing conditional logic at a very, very basic level, and then start expanding from there out to more complex use cases.
And the last question, so I'm as non-technical as you can imagine when it comes to coding, etc. Is there a way for me to get a glimpse of how quantum computing is currently working and testing things out, or do I have to develop my technical capabilities before?
Well, that's why I was mentioning the notebooks. Notebooks are very helpful because you don't necessarily need to understand a whole lot. You can just play around with a notebook, and we have some, for example, on optimization, where the use cases can be, let's say that you know nothing about programming, but you know your business in growing, brick and mortar store distributions, and you want to assess within a given geography how do you maximize how many stores you're placing without putting them too close that they start competing with one another. And this optimization problem is the kind of thing that on Aquila, our first system, the one that is available online through Amazon Bracket, you can start playing around.
Okay, perfect. Just that everybody interested knows how to get into something, because I know if I understand something a little better, I just have my mind wrapping, including these information and some other thoughts, mm-hmm. and then I'll get a bit more creative on what to do. So whoever wants to test it out, I'll link to your LinkedIn profile. That's not for testing it out, but for understanding a bit more, because you're posting once in a while. Then I'll link to QuEra, the website, if somebody wants to check this out, and I'll link to the AWS site, because I think it's helpful to understand, okay, do we want to use it? Do we want to test it out? Alex, it's been such a pleasure. Thank you for joining me here at the Unicorn Bakery. I would offer you the last words of the show to all the founders listening, and then, just a huge thank you from me.
Thank you, Fabian. It's been a pleasure, and thank you for the opportunity. In terms of last words for founders, keep on doing what you're doing. We're changing the world little by little, and it can be a daunting task, but by focusing on creating value for others and building the right teams, I think that there's so much that we can do.
Thank you, Alex.
Thank you, Fabian.